if u equals to f of x comma y is a homogeneous function of x and y of degree n in an open region having continuous partial derivatives, then the theorem says x into dou f upon dou x plus y into dou f upon dou y equals to n f, where n equals to degree of the given function. Since f of xy is a homogeneous function of degree n, hence f of x comma y can be written as x raised to n f of y upon x. Let us call it as a equation number 1. First, we will be differentiating partially with respect to x, and after that we will be differentiating partially with respect to y. Before moving ahead, I want to make a revision. Differentiation of u into v with respect to x equals to u into dv by dx plus v into du by dx. This formula I am going to use to do differentiation of above equation number 1. Therefore, dou f by dou x equals to x raised to n differentiation, that is partially with respect to x, of f of y upon x plus f of y upon x into differentiation of x raised to n with respect to x. Equals to x raised to n f dash y upon x into partial derivative of x of y upon x plus f of y upon x as it is, and differentiation of x raised to n is nothing but x raised to n nothing but n x raised to n minus 1. We know that partial derivative of 1 upon x with respect to x equals to minus 1 upon x square. In the next step, what I am going to do here it will be changing. So here is a y is there, so y will be coming out because we are doing partially with respect to x. Therefore, partial differentiation of 1 upon x, that will be equals to 1 upon x derivative is minus 1 upon x square. So it will become minus y upon x square. Therefore, next step, x raised to n f dash of y upon x into minus y upon x square plus f y upon x into n x raised to n minus 1. Rearranging n x raised to n minus 1 into f of y upon x. What I have done? This positive term I have written first. Then after that plus x raised to n upon x square f dash of y upon x into minus y, that is equals to n x raised to n minus 1 f of y upon x minus x raised to n upon x raised to 2 into f dash of y upon x into y. Here was the minus, so I have taken here, which is equals to n x raised to n minus 1 into f of y upon x minus x raised to n minus 2 f dash y upon x. This is nothing but result of dou f by dou x. By mistake I have not written y, So here is a y which is equals to nx raised to n minus 1 f of y upon x minus x raised to n minus 2 into y into f dash y upon x. Here also y, by mistake it was not written. Multiplying both side by x, so x into dou f by dou x equals to x into the entire function, that is nx n minus 1 f y upon x minus x raised to n minus 2 into y f dash of y upon x. Now this x will be going inside, so this is equals to nx raised to n minus 1 plus 1 f of y upon x minus x raised to n minus 2 plus 1 into y f dash of y upon x. Finally what we get here, nx raised to n into f of y upon x minus x raised to n minus 1 into y f dash of y upon x. This is nothing but x into dou f by dou x. Let us call it as the equation number 2. Now we are going to take the equation 1 once again, but now we are going to do partial differentiation with respect to y. Now differentiating f partially with respect to y equals to partial differentiation of x raised to n into f of y upon x with respect to y. So when we are doing with respect to y, x has no role to do. X raised to n is taken outside. Partial derivative of y upon x with respect to y, that is equals to f dash of y upon x into partial differentiation of y upon x with respect to y again, that is equals to x raised to n f dash y upon x into partial derivative of y with respect to y is equals to 1, but x will remain as it is. Therefore finally what do you get here, x raised to n upon x into f dash of y upon x, which is equals to x raised to n minus 1 f dash of y upon x. Let us call it as a equation number 3. Thus dou f by dou y equals to x raised to n minus 1 into f dash of y upon x. Now multiplying both sides by y, so y here and the y here, so let us call it as a equation number 4. Thus we have equation number 2 and we have the equation number 4. So what we are going to do now, I am going to add equation number 2 and going to add the equation number 4. So adding equation 2 and equation 4. So I am having equation 2 and 4. Now I am going to add them, and what I do, observe that this and this get cancelled, being equal, and one is positive and another is negative. Now what is left? X into dou f by dou x plus y into dou f by dou y equals to nx raised to n into f of y upon x. Now at the end I want to recollect the information we had in equation number 1, that is f of xy equals to x raised to n into f of y upon x. Observe that at RHS there is a capital F and at LHS there is a small f. Therefore this much part can be replaced by f of x comma y, small f of small f, and here is a capital F, so converting to the small f of x comma y. implies x dou f by dou x plus y into dou f by dou y equals to n into f of x comma y. Thus, Euler's theorem on homogeneous function for two variables is proved by using this idea, and by this proof and this concept, let us also talk about a corollary of Euler's theorem as follows. According to corollary of Euler's theorem, if u equals to f of x comma y is a homogeneous function of x and y of degree n in an open region R having continuous first and second partial derivatives, then we have to prove x square dou 2f upon dou x2 plus 2xy dou 2f upon dou x dou y plus y square dou 2f upon dou y2 equals to n into n minus 1 f. Now let us prove this corollary to Euler's theorem as follows. Now from the previous discussion, we are already having x into dou f upon dou x plus y into dou f upon dou y equals to nf. Let us call it as a equation number 5. Now differentiating partially with respect to x, that is partial differentiation with respect to x of x dou f by dou x plus y dou f by dou y equals to partial differentiation of nf with respect to x equals to x into dou f by dou x plus y into dou f by dou y equals to n is constant taken outside dou f by dou x. Here I am going to use product rule of differentiation. So x into partial derivative of dou f by dou x plus dou f by dou f as it is, and here partial derivative of x with respect to x. Here I had utilized product rule of differentiation. Here is y is outside and here is dou 2f upon dou x dou y equals to n into dou f by dou x. Now let us write properly x into dou 2f upon dou x2. Some people call it as a dou x2 or dou x square. I do call it as a dou x2 because we are doing the differentiation second time. Dou f by dou x dot 1 plus y into dou 2f dou x dou y equals to n into dou f with respect to x. Now taking this part to the RHS, so we do get x into dou 2f by dou x2 plus y into dou 2f dou x dou y equals to n into dou f by dou x minus dou f by dou x. So this gives x dou 2f by dou x2 plus y into dou 2f upon dou x dou y equals to, now here is dou f by dou x taken common. Some people call it as a daba also. I do call it as a dou. I don't call it as a daba. I call it as a dou. Okay. So let us call it as a equation number 6. Now multiplying both sides by x. So here is a x. Multiplying both sides by x. So equation becomes x square dou 2f by dou x2 plus xy dou 2f dou x dou y equals to x into dou f by dou x into n minus 1, which can be written as n minus 1 x into dou f by dou x. Let us call it as a equation number 6. Instead of this, let us call that as a equation number 6. Once again, I am going to use the equation number 5. Now, I am going to do partial differentiation both sides with respect to y. That is partial differentiation of x into dou f by dou x plus y into dou f by dou y equals to partial differentiation of nf with respect to y. Here we do get x into dou to f upon dou y dou x, but here in the second part I have to do the product rule, y into partial derivative of dou f by dou y with respect to y plus dou f by dou y as it is partial differentiation of y with respect to y equals to n into dou f by dou y, implies x into dou 2f upon dou y dou x plus y into dou 2f upon dou y2 plus dou f by dou y equals to n into dou f by dou y. Now, in this case, I am going to transfer this to the RHS. So, I get here x into dou 2f dou 2f upon dou y dou x plus y into dou 2f upon dou y2 equals to n into dou f by dou y minus dou f by dou y equals to x into dou 2f dou y dou x plus y into dou 2f dou y2 equals to, here is dou f by dou y is a common, so I do get n minus 1. Now multiplying both sides by y, so x into y dou 2f upon dou y dou x plus y square dou 2f upon dou y2 equals to y into dou f by dou y into n minus 1, writing properly n minus 1 into y dou f by dou y. Call it as equation number 7. Now we are having two equations. What are the two equations? One is the equation number 6 we are having, and we are having the equation number 7. What I am going to do now, I am going to add the equation number 6 and I am going to add the equation number 7. Since the first and second partial derivatives are continuous, therefore dou 2f dou x dou y is equals to dou 2f dou y dou x. Therefore, in the equation 7, I am going to change y to x and x to y. Therefore, on adding x square dou 2f by dou x2 plus y square dou 2f by dou y2, here 1xy plus 1xy equals to 2xy, and this is the dou 2f by dou x dou y being common, it will be the dou 2f upon dou x dou y equals to, here n minus 1 is common and x into dou f by dou x plus y into dou f by dou y, bracket close here. But x into dou f by dou x plus y into dou f by dou y equals to nf. So here this much part I am going to replace by nf. Therefore x square dou 2f by dou x2 plus y square dou 2f by dou y2 plus 2xy dou 2f dou x dou y equals to n minus 1 into nf. This can be written properly, n into n minus 1 into f. Hence, corollary to the Euler's theorem has been verified.